Well, just to reassure everyone, I think this first one is actually one of the hardest one. But so let's try with this one. So first, let's just read carefully what's going on there. And of course, the idea is that it's live. So I have two computers. I have my eyes on the chat, and I'm waiting. I welcome any interruption or questions. And Sean, of course, if you make some comments, you would have done things differently. You want to specify things. Interrupt me all the time. That's what there are two of us. Okay, so we said, so we're given a drawing, and we are told that these three dots here represent the cube roots of 1. So that means when we raise them to the power of 3, we get 1, and we totally believe that. 1 cubed is indeed equal to 1. We know some things about the cube roots of unity. These were drawn, not very visible on the screen, so I just add them. And so we know that they're supposed to be on a circle. They are, and they're supposed to be evenly spaced. Okay, so far, it's like they solved the equation for us, and this is the result. So let's do the first question. Show that if omega is a cube root of 1, that means omega could be either of those three complex numbers. So we want to do a general proof for all of them. So let's just write what it means. Omega is a cube root of 1. What it's telling us is we know that omega cubed is 1. Okay? And if that's the case, we need to show that minus 2i times omega is a cube root. Again, if it helps you, you can write what the goal is. What's required to prove, RTP means required to prove, is that it's a cube root. And the definition of something is a cube root is when you raise the thing to the power of 3, you get, well, a cube root of y, a cube root of 8i. So when you raise to the power of 3, you get 8i. I think for this first part of the question, you probably realize that writing down what the definition of cube root is basically gives you the strategy. You want to show that this is true, so just take a number, you raise it to the power of 3, and if everything goes well, you will get 8i. So let me do that. So minus 2i omega to the power of 3. Well, if I raise each of them to the power of 3, and since I don't want to be the only one working here, in the chat I would like to know what minus 2 to the power of 3 is. Minus 8? Yes. So of course, I'm going to ask the next term. What is I cubed? Simplify as much as you can. Yes, minus I. You're going to use the first two i's to get minus. We're getting minus I. What's omega cubed? Yes, it's 1. So you don't know what omega is because it can be either one of the cube roots, but you know it's a cube root. And if you were careful enough to write what the definition is, omega 3, sorry, omega cubed, so we know it's 1, that's what you said. And so we're getting minus 8 times minus I. Don't tell me my pen is going on strike. We're getting 8i, which is what we want. Question on this one? Hopefully the stress goes down. You just need to see what the question wants you to do. Okay, now something new. So they're telling us we need to rotate and scale the diagram to put, so the goal is to plot and label the cube roots of 8i. So of course we could actually try to find them, but I don't think that's exactly the spirit of that question. Because above, what we did above was to say, if something is a cube root of 1, so these are drawn for you already. If you just multiply by minus 2 times I, you're going to get a cube root of 8i. Right? So what we're going to do, we're going to start from 1 omega, which is drawn. We're going to multiply it by minus 2i, and that's going to be a cube root of 8i. And we can do this for each of them. So we would love to know what geometrically multiplying by minus 2i does, right? And since they're talking about rotation, does it point you towards the polar form or the Cartesian form? Are we scaled? So the question is, indicate the scaling and the angle of rotation. Do you think we should be working in polar form, or we're working in Cartesian form, which is a plus ib? Yes, polar. Because angle, if you rotate, you're really looking at the angle. So the polar form looks at the angle. And scaling means, for example, all the distances are multiplied by 3 or divided by 4 or something like that. And that's something you would see on the modulus. So with this in mind, let's see. So in general, we want to know what it does to any number omega. So omega is a complex number, which we can write this way. And if you multiply it by minus 2i, you know what would be is if you could write for me minus 2i in polar form, because if I'm going to be multiplying two numbers, one is in polar form and the other one is not, it's inconvenient. So you pull out a piece of paper, you draw the minus 2i in there, and in the chat, you tell me what minus 2i is in polar form. So that means you put it on your drawing, and on your drawing, you're telling me how far away it is from the origin. That's your modulus. And what the angle is. That's almost a polar form. Your polar form should contain two pieces of information. So Andy, can I get the second piece of information? Yes. The distance is 2. Yes, so Alec has the perfectly correct way of expressing things. The distance is 2. And this angle, because, okay, we decided in trigonometry, we always measure all angles from there, and we decided that if we go this way, this is counted as positive. We decided that's what positive is. Sailors with bearing decided otherwise, but we were here first. Trigonometry exists since ancient Greek, so we win. And so in that case, that's a minus pi on 2. Okay, so you told me the distance is 2, the angle is minus pi on 2. And I lost my r exponential of I theta. So I'm going to put together the constant, get 2r exponential of I theta minus pi on 2. I'm going to leave in a space. So the modulus was r, and now it's 2r. What happens to the distances? See, I started with something which was r units away from the origin, and now I'm getting points which are 2r units away from the origin. So what's the scaling factor? Scaling factor asks you, by what number have the distances been multiplied? They have been multiplied by 2. When you go from r to 2r, the distances have been multiplied by 2. Now, if the position, okay, so the position of your point was given by this angle theta, and now you change it to theta minus pi on 2. So, okay, so we always start here, and to go to the new position, we do theta first, and then minus pi on 2. Let me try to get. What's my angle of rotation? So that would be my omega, and my 2 omega would, sorry, my 2i minus 2i omega would be somewhere on this line. What rotation did I perform? What's the angle of rotation? You can imagine I take this, and to bring it in the new position, that's the new position, I need to rotate clearly. Did I rotate by something positive or negative? To go from the old where omega is to the new one. I even wrote the angle of rotation. So you can look at the drawing, or you could say I have theta, and now I have theta minus pi on 2. What's the angle of rotation? Minus pi on 2. Thank you. So my angle of rotation is minus pi on 2. So I'm going to use this to get the answer, to draw the cube roots of AI on the new drawing. So it tells me I need to multiply all the distances by 2, right? So for example, this first root, 1, it was 1 unit away from the origin. So now the root I'm going to create from that will be 2 units away, right? So there's the distance, so maybe 2 is here. be the same thing for all of them. This also was 1 unit away from the origin. This was 1 unit away from the origin. And we said all the distances are multiplied by 2. That tells me that all my new routes will be on a circle of radius. Well, okay, you didn't need any of the things we did right now to find this out, because you know already that all the cube roots are always on a circle, and in that case it was easy to calculate the radius of the circle. So I'm going to put that. Okay, so I've used the scaling factor. Let's start with this one. I want to know where it goes. So the game was, so I multiply by minus 2i, so I multiply the distance by 2, so I got there now. And now I need to rotate by an angle of minus pi on 2. Where am I going to end? So in that case, you can calculate, but you should also see the angle. Where will 1 go if I multiply by minus 2i? Maybe the question is so obvious that you don't dare. And on the negative y-axis, yes, it's going there. So here I get minus 2i. And you can see that's what we did. So we tried to do it geometrically. We multiplied the distance by 2, we got it, and then we rotated by minus pi on 2. I started with this one because it was the easy one. So this one came here, right? And if in your head you imagine in 2 steps it's easier. Step 1, make a drawing, multiply all the distances by 2. This one will come here, this one will come here, and this one will come here. Step 1. And now imagine you grab this drawing and you rotate it by minus pi on 2. This one will come at this position down there. So this was just an intermediate step. So I'm going to erase this little dot there. That's an intermediate. And it comes here. Can you predict what? Try to see in your head. So maybe it's hard. I can't ask you to draw it in the chat. But imagine you're really grabbing the thing and rotating. What will it look like? And one way for me of knowing if you've got the right picture in your head is, once you multiply all the distances by 2 and you're rotating by an angle of minus pi on 2, is there an axis of symmetry in what you get in the end? If there's one of symmetry, you tell me what it is. The y-axis, yes. Okay, so people really see it. So what I can see here, this angle here, this little angle here, is going to be pi on 6. And so if I rotate, it's going to come there. Right. So here I'm going to get this axis of symmetry. So I'm drawing the axis of symmetry. And I said the distance would be 2. So this one, if it like came here, and this one came there. So I could say that, is that all they wanted? And so what did they want? So we drew them, plot and label the cube roots. So I don't know what they want exactly. If they only want, so for me, I would be happy for people telling me, that's how I got this one. Because really, once you explain the scaling factor, you did the geometry, 2i pi on 3, right? And so this one would be minus 2i exponential of minus 2i pi on 3. If you label it this way, it's clear which root went where when you move things, right? And so, of course, it would be easy to calculate them. But because of the wording of the question, which is very geometric in terms of angle of rotation and scaling factor, I think it would be just fine to stop there, provided you indicated what the angle was and what the scaling factor was. Now, of course, once you've done that, it's not very hard to actually calculate what they are, and we could do this if we see that we need this later on. And also, I wanted to do it very geometrically because I'm pretty sure that you would be comfortable doing the calculation, whereas thinking of this in terms of geometry is probably harder, right? Axis of symmetry. Question on that? Or maybe I finished the calculation so it helps us check. Yes, please. Turn on your microphone, Eric. I'm listening to you.
I'm sorry, does this work?
Sorry?
Can you hear me? Can you hear me?
Yes.
Right. I'm just a tad bit confused. Would like to clarify some stuff. So the question is asking, See, when it says hence by rotating and scaling the diagram above, plot and label the cube roots of 8i.
Yes.
So I understand the part where you got the so you know that from the value -2iw, and then from that you can find the modulus and the angle of rotation.
Yes.
But I'm confused about how you know just the question's wording. What I would have done in an exam situation is just plot that onto the graph without the rotation part.
Oh, yeah, but here it says indicate the angle of rotation and the scaling factor.
So we would have to say like it has the modulus of it would scale by 2 and it would rotate
Minus pi on
pi minus pi on 2.
in the yes. If the question was only plot and label the cube roots of 8i, I think no one would even think of doing probably geometry. They would probably just solve the equation, find what the cube roots are, and plot them without using the cube roots of 1.
Could you also explain why the modulus scaling factor is 2 and not -2?
Because usually a scaling factor is positive. By how much do you multiply or divide the distances? I guess if you said that it's -2 and then you put a different angle inside, so you have to be consistent. If you multiply by -2, okay, too many drawings there. I'll redo one. If you start with 1, so that's your 1, and you say I'm going to multiply this. I'm going to multiply by -2. You get there. And then you can apply a rotation of plus pi on 2, and you would end up in the right place. So I think so usually scaling factors are positive, but if someone told me that really what you are doing is saying that this is -2 times exponential of I pi on 2. So you're saying I'm multiplying, so if I multiply this by omega, so it's a -2i. If I multiply by omega, my omega. Here I'm going to get an r exponential of I theta. So what you get here is -2r. So if you'd like, you multiply this by -2, and you added pi on 2 to your angle. If you're consistent, you could do that, but see, the wording also is going to be more difficult. I multiply the distances, so I multiply the modulus by -2. Now what you get is no longer a modulus because it's negative.
I'm gonna have to review on that, but yep, thanks for your help.
Yeah. So then maybe in order to check what we've done, we could actually calculate the Cartesian form, and some people will probably be comfortable if it goes back to what they know. So exponential of 2i pi on 3. So we know, so it's really cosine 2 pi on 3. Sorry, so for this one. So it could be this one, if we start from this one. I'm sorry, sometimes my pen writes and sometimes it doesn't. Okay, so it's happy to write there. Worst unit circle ever. Let's do that. So pi on 3, and then you will. So I think there was some question about the formula sheet. It will be the usual one you have in every exam, meaning there's almost nothing on it. There's only the integrals and nothing else, right? So if that's your exponent, so in particular, what I'm trying to tell you here is you will need to know the famous values for trigonometry. And you can do this either using the unit circle, or you can also do this using the famous triangles. For me, what I know is if it's pi on 6 or pi on 3, one of the distances seems to be close to 1/2, and the other one seems to be close to 1. The one close to 1/2 is actually 1/2, and the one which looks close to 1 is square root of 3 on 2. So what I can see here is that my x-coordinate is negative, so that's a -1/2. The one that seems to be close to 1 is square root of 3 on 2, and in that case I can see it's positive. So what I'm getting here, my I squared will give me a -1 with 1, so I'm getting square root of 3 plus, when I multiply, square root of 3 plus I. Well, that's consistent because indeed I can see on my drawing, if I look at this point there, that the x-coordinate and the y-coordinate are both positive. That's the first good thing. And I also can see that the x-coordinate is larger than the y-coordinate. So all this looks good. I can do the exact same thing for the other one, minus 2i. And so again, I'm going to use a unit circle, use whatever you like. I like to advertise a unit circle. Once you understand this, everything works. So here, so pi on 3 is all of that, minus 2 pi on 3 is going to be there on my circle. One of the coordinates seems to be close to 1/2. It's the one on the x-axis, so I know that my cosine is plus or 1 minus half. And I can see on the drawing it's negative because it's the x-coordinate, that's my x-axis. And I can see that sine, which is the y-coordinate, is going to be negative also. And it's the one which is close to 1, so it's close to 3 on 2. Okay, so let me simplify again. Let's find the real part of that. Since I is minus 1, minus times minus is plus, I'm left with minus square root of 3, and then plus I. And I can check on my drawing that indeed I'm very happy to get a negative x coordinate for that point and a positive y coordinate, and that the x coordinate in absolute value is larger than the other one. So in fact, we ended up calculating also the cube roots. So just to reassure the people who would have done it this way. But if you only calculate them and then plug in on your drawing square root of 3 plus I, minus square root of 3 plus I, and minus 2i, you didn't really answer the question. Because see here it says nth. So that means the only solution which will be accepted is one that actually uses the square root of unity. Right, so let's move on to the last question. We can clear this up. Explanation for the question. So we want to find z such that when you cube z plus 1 minus I, you get 8i. What can you tell me about z plus 1 minus I? Can be in plain English. This equality tells you what? Just to see if you recognize that the different parts of the exercise fit together. I should put all that. Yeah, so I want you to see all the questions in front of you. They're telling you that z plus 1 minus I, when you cube it, gives you 8i. If you were to turn this into a sentence with only is a cube root. Yes, it's a cube root of 8i. We know the cube roots, we just calculated them. Therefore, z plus 1 minus I could be either the cube root at the bottom, minus 2i, or it could be, so then I go to my drawing where I calculated things, square root of I plus 1 for z, sorry, that's my pen, z plus 1 minus I could be square root of 3 plus I, or z plus 1 minus I could be minus square root of 3 plus I. There are exactly 3 square roots of unity, and you know that z is one of them. Then you can just solve that. It's going to be fairly easy, and we will see what we get. So that means, or maybe you do it for me. And just to make it easier in the chat, I'm going to call the first one Z1, the second one Z2, and the third one Z3. And I'm going to take a little break, and in 10 seconds in the chat, I will have all of them. So give me Z1 first. Z1. So you said minus 1 minus I. I agree with you. What about the Z2? Ideally, someone who's not Alec. Come on, you can find Z2 for me. We're just solving. It's just make Z the subject, and then you will find what Z is. So you said square root of 3 minus 1 plus I. Yes, so this 3 is on the right side. I subtract 1 from both sides plus 2I. And what do I get for Z3? If you did Z2, you can do Z3. So square root of 3 plus 1. I was getting something different. Maybe I did something. So you get, there was a minus in front of the square root of 3, right? So you still have this as square root of 3. Maybe a different color. Yes, I'm getting minus square root of 3. Yes, indeed. Minus square root of 3 plus, so minus 1, not right anymore, plus 2i. Okay, well, let's imagine I wrote plus 2i, because I can't write anymore, everything's freezing. Which one is the solution? You tell me that, chat. Go back to the question, Z2. Yes, the question says that we want the real part of this word. We want the real part to be positive, square root of 3 is 1.7. So in that case, this is positive, this is negative, and this is going to be negative. So your solution will be this one. And see, it's important that in the third question you notice that we are really talking about the cube root of 8i and already have done, because otherwise the temptation would be to solve again, and that would be a big waste of your time. Do you have a question on this one? I think it's the hardest of all after doing them all. Okay, so Sean, I'm going to go out and restart my computer because I can't, yeah, it's getting really hard to write. So I'll let you take over.
Sure. Yep, okay. All right, so yeah, hopefully everyone's happy with that question that Laura just went through. Oh, just one thing I was going to mention at the end of that is another thing. Well, hang on, let me just share my screen, which should have the same writing that Laura's just done. Okay. So another way that you might have found which of the three roots you wanted for this last part of part 3, if you were being very clever, is think about what Z should look like on your diagram. So if Z had 1 plus I added to it, so over here, this is Z plus 1 plus I, to become a cube root of 8i, then the idea is that you're kind of traveling 1 unit to the right and 1 unit down from your potential Zs. So my Z might be up here somewhere.
It's still my screen, it's not yours.
Oh, hello? So I think Laura might have restarted now. I'm just checking the chat. Can people still hear me? Yeah? Okay, cool. So yeah, so I just want to point out, whichever one of the Zs is the correct answer, well, there are 3 possible Zs for which when I add 1 and then subtract I from it, will point me to one of the 3 cube roots, right, of 8i. So my Zs kind of live in these 3 spots. So if I want the Z that has a positive real part, it will be the one to the right of the y-axis. So again, by looking at the diagram, I can find the Z that I want to answer immediately, and then I can just calculate that one, which might save you a little bit of time if you thought to use the diagram. But I think the algebraic approach is probably the one that most people would use here. Okay, so let me move on then to our next question. So this is from the same paper, of course, question 1, part F. So the first thing you'll notice with this sort of question is that it starts with a big dump of maple code. And I know that sometimes students run into these types of questions and get a bit worried that it looks too complicated or too long. But often these problems that start with a bit of maple code are a lot more approachable in some cases than ones that don't. And why is that? Well, usually it's because the maple code is doing part of the problem for you already. It's usually doing the annoying, calculation part to make sure that you don't make that mistake when you have to calculate things yourself. And so the key thing is just to be familiar enough with Maple to know what the output's telling you so that you can use it in the question. So the first thing I would do here is read through this Maple code, and it's pretty clear what's happening, right? Of course, we just introduce the linear algebra package. That isn't very interesting. We define two vectors, v1 and v2, which are given here and here, of course. And then the really only interesting thing that's happening in this Maple code is that the cross product is calculated for us, right? So the first thing I would do before I even start considering answering the other parts of the question would be to just write up what I know from the Maple code. So I can just say from the Maple output, we know, what do we know? Well, exactly what's written in that last line, we know that v1 cross v2 is this vector here, 271. So that's really useful, right? We will probably need to use the cross product somewhere else in this question, and now we don't have to calculate it, because you might know from experience that calculating the cross product of two vectors can lead to lots of sign errors and things like that. Well, we have the answer here now, so we don't need to worry about that. Okay, so now let's actually look at the question, right? Part 1 here is saying that we have a plane P0. It goes through the origin. It's spanned by the two vectors that we've been told about, v1 and v2. And we want to be able to describe any vectors, b, that lie in that plane. So you might like to sketch out what's happening here before you do anything else. So in this case, we have the origin. Whoops. Okay, that's an O, right? We have the origin. And we have two vectors, v1 and v2. Who knows where exactly they point, but they point from the origin. And we're talking about the plane P0, which is sort of, it's of course extending infinitely in all directions, but v1 and v2 span it, and it goes through the origin, right? So it's not the easiest thing to draw, but just for a sketch, that's probably good enough, right? What else do we have here? Well, we have from the Maple output v1 cross v2, and can someone tell me in the chat geometrically if I call, well, yeah, geometrically, what should this cross product v1 v2 v1 cross v2 look like? Yeah, that's the magic word, right? So as everyone's pointed out, that's the normal, right? So I might even define n, the vector n, to be the normal, the cross product of v1 and v2. And so if I imagine my diagram, it's kind of sitting up here, pointing out of the plane at right angles to both v1 and v2, right? Okay, so that's all the information sort of summarized in a diagram. And then the question is, how do I describe any vector b that lies in this plane? So let's draw a sample one for fun. There's a vector b, and it's again, it's hard to draw in these sort of three-dimensional circumstances, but the idea is that it's lying in the plane. It's along with v1 and v2, they're all parallel to that plane, right? And so what is the like, b can be any vector, right? That's in the plane. It might be this one over here. There's another b, right? B dash or something. But no matter what b I choose, what property will always be true for b that involves one of the other vectors that I've drawn in this diagram? Yeah, perfect, Alex. So I know that n dot b, right, the dot product of n and b will always be 0. Why is that? Well, if you couldn't see it immediately, that n vector I drew, the blue vector, it's at right angles to v1 and v2, and indeed it's at right angles to any vector in the plane, right? So there's a right angle here, there's a right angle here. And what do we know about two vectors that are perpendicular to each other? Their dot product must be 0, right? So to sort of summarize that diagram, what we've said is for any vector b in the plane,
And I think that example illustrates really well what you were saying, Sean. You know before starting the question that using the cross product will be useful. So actually the maple output guides you. And even if you
Yeah,
had
that's
never
right.
seen maple, you don't like maple, I'm sure you can guess what the instruction cross product does, you know? Probably calculates a
Yes,
cross
that's right.
product. So yeah, no stress.
Yeah. Yeah, so that's the fact we know, right? And now we can just plug in the vector that Maple gave us, right? B dot 271 is 0, right? But I can expand out this dot product, of course. We've been told that B is, well, sorry, that should have been a highlight. B has the components B1, B2, and B3, right? So the dot product is just going to turn out to be, of course, 2B1 plus 7B2 plus 1B3, right? And we know that that must equal 0. Okay. And that satisfies what's needed for this question part, right? We've been asked to find a condition on the components that's confirmed that B lies in the plane P0, and this is exactly a condition on the components, right? We have this condition that 2 times the first component plus 7 times the second plus 1 times the third must equal 0, right? And whenever we have 3 components, B1, B2, and B3 that satisfy this property, we'll have a vector B that lies in the plane, and vice versa. If we have a vector B in the plane, its components will satisfy that condition. Okay. Are there any questions about that derivation? No, it looks like the chat's not, like nothing's popping up in the chat.
No,
So,
I
oh
think
yeah.
they're just convinced, and maybe they're starting to think, oh, these new exams with maple in it. Actually, there's something good about that.
Yes, yeah, I agree. Oh, and maybe another thing, maybe another thing worth pointing out is that you might recognize this diagram as the way that we derive the point normal form for a plane in general. So you might have preferred to use that, right? Like a sort of, it's sort of the same approach, but a sort of alternative method might have been to say, by the point normal form of the plane, any vector in the plane, so any vector B dot the normal vector n must equal the normal vector n dot any point in the plane, or rather the direction vector for any point in the plane, right? And of course, we know one of the points on the plane is the origin, which is how we get 0 on our right-hand side. Okay.
But I prefer what you did initially. It's more geometric. I think it reinforces
Yes, I
the
agree.
idea. But in math, if you have the picture in your head, you don't really need many theorems. Just look at the picture
Yes,
in your head
exactly.
and that's it.
Yeah, I agree. And I don't know if I would have immediately known to think of the point normal form. Like
I
it's much
wouldn't,
easier
and
to
I
start
think
with
it
this
would,
diagram.
yeah.
Yeah, yeah.
And Raphael, I agree with you. Let Maple do the dirty work and we'll do the thinking. Yeah.
Yes, exactly. Yes. Okay, all right. So let's move on to the second part then, and it's actually sort of similar. It's going to follow the same sort of ideas. So this time we've been given a plane. It's a different plane to the first one, right? Or at least it's explicitly we've been told that it's not going to necessarily be the same as the first one, right? Because we're talking about plane P1 this time, not P0. And this time the equation for the plane has been given to us, and it's in vector parametric form, right? So the question simply asks us to convert or rewrite the plane in a Cartesian equation form. And this is probably a type of question that you've encountered a few times in lectures or tutorials anyway. But
Yes, and past paper. There's nothing original about this one. Yeah.
yeah, I wouldn't think so either. So, but can anyone tell me? So usually there's a useful stepping stone, right? We've been given the vector parametric equation. We want the Cartesian equation form. What is another form of the plane that can be a useful stepping stone when we're converting between one and the other? Yes, Eileen. Yeah. Let's try to find the point normal form first. So that also might have been hinted to us if we were thinking about how we solve the first part of the problem, right? So to find the point normal form, what do we need? Well, we need a point through the plane, and we need the normal to the plane, right? Well, a normal to the plane is going
That's
to
when
be
you
what?
realize the question I called little I and little I. That means they are part of the same exercise.
Yes. Yeah, that's right. So because how would I find a normal to the plane, right? Well, I would take the cross product of the two vectors that are multiplied by the parameters, right? But these better be, well, these should be very familiar to you because they were exactly what V1 and V2 were defined to be at the top of the problem. Yep. So I notice that this vector here is just V1 and this vector here is just V2. Yep. So yeah, as the law said, just because it's a new part, it's still part of this overarching Maple question. How does it relate? Well, this is the relationship. Okay, so a normal to the plane is going to be the cross product of those two vectors, v1 cross v2, and hey, we already know what that is thanks to the Maple output. It's 2, 7, 1. Okay, what's the point on the plane? Well, there's one given to us in the vector parametric form. So this vector here tells me that 1, 2, 3 is a point on the plane, or on the plane P1, right? So those are the two things I need: the normal and the normal to the plane and a point on the plane. And so I can just substrate in to my point normal form. So remember that will be that n dot x, where x is the general vector, equals n dot a, say, where a is the vector representing a point on the plane. And so I'll just substitute in. So my n I know is 2, 7, 1 dot x, and my right hand side I'm going to get 2, 7, 1 dot 1, 2, 3. And can someone in the chat calculate that for me? What that right hand side will be?
I'm not very good at mental math, and I have it. So don't be. Yes, Alec, thanks. 19. Yes.
Yes, thank you, Alec. Yeah, so it's 19. So yeah, just in case you're a bit rusty, don't forget this is 2 times 1 plus 7 times 2 plus 1 times 3. But yeah, so that's 19. Okay. And so just to make it super clear that I have a Cartesian form, I can just expand out x, the vector x, with its components x1, x2, and x3. So the left-hand side is 2x1 plus 7x2 plus just one lot of x3 equaling 19. Okay, and that is the Cartesian form.
Can you write is a Cartesian form? Because if you multiply everything by -3, it's more complicated.
Yeah,
it still works.
true.
And I don't like that about the question. We shouldn't have left it there.
Yeah,
and
yeah,
also,
true.
That's something we're discussing with Jonathan in class. It's Cartesian means there's no parameter. So really, for me and him, a point normal form is a Cartesian one. Then there's the expanded Cartesian one, and the point normal form is just a special case of Cartesian equation. So
yeah, that's
but, well,
a good point.
yes,
Yeah.
I know what they wanted here. Yes, it was exactly what you got.
Okay, good.
Okay, so done with this one. And so you see, I told you the one I did with the geometry, they were really trying to push you to use geometry in complex numbers, was hard. I think these others are much, much easier. Okay, so let me share my screen again. If you have questions for Sean, you ask them right away while I'm sharing my screen. Can I click, or 3, 2, 1, no question for Sean? Moving on. So the next one is another geometric one. So we have a line and we have a plane. So I tend to not be able to do anything until I see what's going on. So I have a plane, yes. From the plane, what's easy to get to define my plane? Sometimes it's easy to get, if it's parametric vector form, it's easy to get two vectors and a point. When it's given like that in Cartesian form, what can I get very easily from the equation of that plane? Because I'd like to do a smart drawing, not just say, yes, I can get the normal. Indeed, the coefficients there, this 1, this 2, and this 3, give me a normal to the plane. So I'm going to write this. So yeah, let's try to go for a smart drawing in some sense. And then there is a line. Okay, I have a line. What am I going to draw on my line? Same thing. I'd like to indicate what I know about the line. What am I given? So you said for the plane, what I knew was a normal vector. For the plane, what I can, sorry, for the line, what I can read right away is a point, right? And what else? So let's say that's my point. What else can I read directly? What's been given to me because I got a parametric form for this line? A vector which gives me the direction of the line, absolutely. So I call this V, and on my drawing, I'll insist on the fact that I know a vector on the line. So the line is called L, the plane is called P. Okay, so I haven't done anything, but at least I have a drawing which tells me that I have a line for which I know a point and a vector, and I have a plane for which I know a normal vector. Show that the line is parallel to the plane. You're gonna have to give me a strategy. It's fairly close to what Sean did earlier. And if you'd like, try to imagine, take the plane to be your desk, and if a line, and imagine that you have something pointing out of your desk, that's your normal vector. How would you know? How would you know that your line is parallel to that plane? How do I get this? Yes, same thing. You're only interested in the direction, so you could redraw your vector v here. If really the line is parallel to the plane, that means this vector v will need to make a right angle with n. Okay, so let's check that. So L is parallel. So we explain the strategy to the plane P if and only if n dot a is equal to 0. Just something on notation, you can use tilde, you can use arrows, and we'll always understand you're talking about vectors. If you were doing the exam on paper and there was no arrow and no tilde, then we would definitely kill you. I guess this term, it would be much harder because we won't make you write a lot, and so it would be complicated. But just remember, also on your rough working, it's going to be much clearer for you if it's very clear what's a vector and what's a number. So that's my n, and my v was 1, 1, minus 1. So I'm going to calculate this, and I get 1 plus 2 minus 3. I indeed get 0. So therefore, L is parallel to the plane. Okay. And so in case you're worried that Sean and I initially spent a little bit of time thinking, you know, what does the maple output tell me? How can I represent what goes on? The exam's got, you still have the same 2 hours, well, and now you will have 3, but it's 1 question shorter. So you have a little bit more time to think. Jeremy, I'm listening to your question.
Hi, Professor. Just regarding when I saw the Cartesian equation for x1 plus 2x2 plus 3x3, I know this might be not one of the smartest questions, but like I think for if you're given that's the Cartesian equation, it will always be that the normal vector is going to be 1, 2, and 3, something like that, if I'm correct.
Yes, it's always going to be, if I had 7x1 minus 2x3 equal to, I don't know, 19, then my normal vector would be given by those coefficients, and I picked a tricky one. So in that case, I know that 7 minus 2 and 0 would be a normal vector. Yes, it's always the coefficients. And what you get on the right-hand side is irrelevant. It doesn't give you any information about the normal vector.
I believe I think, isn't it, shouldn't it be negative 2 and 0 be switched if it's going to be minus 2x3? Yeah.
Oh, yeah, sorry. I said x2 and I wrote x3. Yes. So right. 0, x3. Absolutely. Yes. So whenever you have, yeah. So, and it's really important to be able to get a normal vector from there.
Thank you.
So no stupid question. And if there are basic things you don't know, now is a good chance to ask, because you really need to have the basic nailed down before you go into the exam. Okay? So ask all the questions that cross your mind. So now we need to find a point on the line. I guess we did that already. See, it was not a waste of our time, because from the beginning, we analyzed the question and we said the point with coordinates 1, -3, 2 is on the line, which I'm allowed to write like that, belongs to the line. It's less obvious for the plane. So first, there's an infinite number of points on that plane. You just need to get one which works. So you need to find 3 numbers. So that would be x1 plus 2 times. So you need to put things in the box. There are an infinite number of possibilities that give you a 4. Can I get at least 2 points in the chat? You don't have exactly. Alex is like me. There's no need to suffer. We can make this easy. If I do 4 plus 0 plus 0, I get 4. So definitely this works. There's another one which is not too hard. Other things you could put in those boxes and you would get 4 without suffering too much. Yes, 0, 2, 0 are nice. Your 2 times 2 gives you a 4. Now, of course, we could, if you want to be fancy, you could do things and put, I don't know, you could put 5, maybe 5/3 here, so that's a 5, and then you put a -5 and a 0. The only reason I'm showing you this one is just to show you that there's an infinite number of solutions. Why have fractions if you don't have to? And I'm going to use the 400 because I bet that's what most people would use. Write down the vector AB. Okay, easy, the vector AB, so coordinates of B, components of B, minus the ones of A, plus 3 minus 2. So I'm getting 3, 3, and -2. Easy question, really. And I can add on to my drawing. So now I have a point B on the plane. Well, I can really draw my normal vector anywhere I like. So maybe I'm going to draw my normal vector exactly where B is, just in case it helps. What happens next? Find the shortest distance between the line and the plane. Okay, so what do I know? So I have my plane, I have my line. I said I had my point B. I can draw my normal vector there. So that's my point B, and I have a point A on the plane. Does looking at the drawing inspire you in some way to find the shortest distance? How could we do that? Projection. Yes, projection. Projection of what onto what? So those who didn't think of that, you can use this idea. So while I write the beginning, so the shortest distance between the line and the plane is, so if we project onto the line, so if I project AB onto the line, so let's say I may get this. So let's assume that they right above each other. I will get this. That's not the one I want. If I project on the line, onto N. Yes, we need to project onto N. So if my normal vector is there, sorry, I changed colors. And then, so here I could get, you know, this right angle. The distance I want is really that. And I could get this by projecting AB or BA onto N. Yes. Now, if you want to be precise, if I said the shortest distance is the projection, it's not exactly correct because the distance is a number and the projection is a vector. Can we improve this? I don't want to write the shortest distance is the projection. It's really related to the projection. Once you calculate the projection, you get that vector. But really, it's a vector. So what do I want about this vector to get the distance? The modulus. Okay, so we use modulus for complex numbers. We use a magnitude or norm for vectors, but that's exactly the idea. Or length is the length of the projection. Of AB onto N. So if you project, let me just draw that. If you project AB, the projection you will get will be this vector pointing that way. And when you calculate the length, you're going to get the shortest distance. Sorry. If you project BA, you're going to get that. So I think for most people, it would be more natural to project BA, but because we already have AB, maybe we just project AB. So once you've had this idea, it's all about drawing. So we want, so these bars, sorry, these bars just mean we want the length of the projection. Projection of what? We project AB onto N. And so we have a formula for that. That you do the dot product of your two vectors. That's why I like my arrows. I don't like a mix of tilde and arrows. Everything that has an arrow is basically a vector. Then you divide by the dot product of the vector you're projecting on by itself. So that's your projection. That's a number, and then you have this N there. Okay, so that's a number, and this one is a vector. So let's do this slowly. So we have AB dot N. So my AB is 3, 3 minus 2. My N, I think, was 1, 2, 3. Where's my N? Yes, 1, 2, 3. 1, 2, 3. Here I'm going to get 1, 2, 3 with dot product with itself. I don't know why I keep writing this bar, which doesn't exist. And then I'm supposed to multiply this by 1, 2, 3. And when I'm done, take the norm. So what do I get? What do I get here first? What do I get at the top? Can you put that for me in the chat? 3. Okay. What do I get here at the bottom? 14. Okay. And so if I calculate the length of that vector, what do I get? Now I need to calculate. So my last bit is the length of that. Yes, it's going to be the same calculation, square root of 14. So some people like to rationalize the denominator, so they will insist that you don't have a square root at the bottom, and they will write it this way. Other people say we don't mind, so both this answer would be correct, right? And so that's what we get, so that's the distance. See, this one is not a particularly original one. I think if you think of drawing, then you really don't have a big problem about what to do. Do we have questions on this one? No? So Sean, I think you can move on and bake some cereals for us, some muesli.
Yeah, okay, sounds good. All right, I'll just share my screen. Okay. All right, so the next question we're looking at here is question 2, part B. And this one it has a big sort of preamble, a little story about a cereal manufacturer making different types of cereal, and they have 3 different names, and they each use 3 different ingredients, and there's just a lot of information to take in at once, right? I think the best way to approach this kind of thing to start off with is to look forward to what you need to do. So, for example, in part 1, I'm being asked to write a system of linear equations in x, y, and z, right? And so next thing I'm going to do is look back at this long story and work out what x, y, and z are, right? And here is where x, y, and z are defined, right at the end of the preamble. They are the number of bags of each of these cereals, I guess, that we're making. And so I'm sort of, maybe I'll use a different colors here. My x is being associated with the number of bags of regular, and regular has its recipe here, right? Y is the number of fruity bags, and that's the recipe for the fruity things, and Z is a number of bags of the nutty example, right? So maybe I'll just write out in sentence structure what happens in terms of these ingredients in each case, right? So if I have X bags of regular, which I might just call big R for now, then what I really know is that those X bags have X seeds in them, right? According to this recipe here, they have 1 lot of seeds per bag. They have 2 lots of fruit. So I know that X bags will have 2X lots of fruit. And they have 2 portions of nuts. So X bags will have 2X lots of nuts. Great. And that's kind of me summarizing that information using X's now, right? And so similarly, I can say the same for what happens with Y and Z. If I have Y bags of the fruity thing, the F cereal, then I'm going to have how many of each? I'll have Y, lots of seeds. I'll have 5Y, lots of fruit. And this time there are no nuts, right? So I could even write 0Y nuts, maybe. Okay. And then I can do it again for Z. If I have Z bags of the nutty thing, so N cereal, then I'm going to have 2 Z, lots of seeds. 1 Z, lots of fruit. And 6 Z, lots of nuts. Okay. So I've really just rewritten the information I already know, right? But I think it helps, by writing out like that, it helped me sort of understand a little bit better how the X, Y, and Zs map to the seeds, fruits, and nuts, right? And so finally, to answer this part 1, I want to write a system of linear equations, right? So I would like to know, well, what haven't I used yet? I haven't used the portions, the number of seeds, fruits, and nuts that are available. So if I do tally those up, right, if I look at my seeds, how many seeds am I using altogether if I make X lots of regular, Y lots of fruity, and Z lots of nutty, based on the information I've written over here, can someone tell me what equation I can derive about just the number of seeds total? Yeah, that's right, Emma. Thanks. So, so Emma's written that we have X plus Y plus 2Z needs to be 126. And hopefully you can see that because how many seeds are there altogether? Well, the seeds turn up here, here, and here, right?
Maybe we can circle in red rather than highlight in purple, because on my screen it almost disappears.
Oh, okay, yeah, sure. Good idea. Yeah, I was thinking it looked a bit dark as well. So the 3 times that seeds turn up, there are X lots of seeds every time I make X, when I make the X bags of regular, Y lots of seeds when I make the Y bags of fruity, and 2 Z lots of seed when I make the Z bags of nutty. So the sum of those things will be the total number of seeds used. And since the goal of this manufacturer is to use all the ingredients for the day, I need that sum to equal 126. Okay. So this magic number here. Okay. So similarly, then I can do the same thing with the fruit portions and the nut portions. So can somebody tell me what's the second equation I should be writing up here?
Yeah, that came up really fast.
I have it already. Yeah. Okay. So we're just reading off the fruit facts this time, right? So I'm looking at how much fruit. Well, there's 2x plus 5y plus z, lots of fruit, right? 2x plus 5y plus z, and I need that to equal 171. And what about for the nuts? Yeah, thanks, Jen. So again, I'm just reading off these last facts. The total amount of nuts is going to be 2x plus 0y plus 6z, and it needs to equal 306. 2x, 0y, and 6z. Okay, so that is our system of linear equations. Okay, and that's all we needed to do for this first part.
And
Are there
thanks
any
to
questions about that?
0y, it helps to notice that there's nothing and keep track and
Yes,
line
I agree.
exactly with your x's and so on.
Yes, yeah. So Laura and I both recommend if there's a 0 involved, still write it out if you're going to be using a matrix at some point. Okay, so let's move on to part 2, and you can probably guess we have a system of linear equations. We're going to want to solve them, right? So part 2 says to use Gaussian elimination to solve this system. So let's write up our augmented matrix and reduce it to row echelon form. So I can read off my augmented matrix from the system of linear equations. So I made sure to line them up properly so that all the x terms appeared in one column, all the y's in another. That was another reason that using a 0y was useful there. So I'm just going to write out the coefficients now. So I've got 1, 1, and 2, and then my dividing bar and 126. My second row is going to be 2, 5, and 1, and 171. And my third row is going to be 2, 0, and 6, and 306 down the bottom there. Okay, and now it's just a matter of row reducing this matrix. Yep. So any suggestions on what my first 1 or 2 steps might be in the aim of making this a simpler matrix? Row 2 to row 2 minus 2 row 1. Yes, I like that idea. And I can see from what people have posted in the chat that there's this confusion that comes up every term about whether you want to point the arrows towards what you're changing the
There's
row
no
to.
confusion. They're using it correctly. Yes. That indicates what you're putting into row 2. But as we said, yes, I think the notes are inconsistent with that. We said for a long time we would change them. We're not going to blame anyone for using the arrow one way or another.
Yes. So I'll use the, well, to me, I call that a backwards arrow, but I'll use that one. So yes, row 2, we'll subtract 2 lots of row 1 from it. And we can do the same to row 3 at the same time, right?
Yeah, that's what
why
Emma
is it
suggested.
safe to, yeah, thanks, Emma. So, and why is it safe? We should always be careful when we're performing more than one row operation at a time. But as long as they're not interfering, we're not manipulating the same row twice in one step, then that's okay. So I can subtract 2 lots of row 1 from both of the rows beneath it. And what will I get? Well, now it's just a matter of crunching out some numbers. So in this case, it turns out to be 0. 5 minus 2 is 3. 1 minus 4 is minus 3. And I want to do 171 minus 252, which I've already done in advance. It's minus 81, right? You will hopefully have your calculator with you to work that out, or you'll be able to do it quickly on a scrap bit of paper. Okay, and what about this third row? Well, same deal. I'm going to subtract 2 lots of row 1 from it. So I'm going to get 2 minus 2 to give 0. 0 minus 2 to give minus 2. And 6 minus 4 to give 2. And that last term, 306 minus 252, happens to be 54. Yeah. Okay, so this is looking a bit better. Of course, the reason we did those first 2 steps was to make the first pivot entry, so to make this one the only entry in its column, or the only non-zero entry in its column, right? What might I want to do next to further simplify this matrix? Any suggestions? Yeah, Emma. Yeah, that's nice. So so there's a suggestion to manipulate rows 2 and 3 with each other in some way. So you could, for example, add 3 lots of row 3 to 2 lots of row 2, or vice versa. I might just do the other suggestion from Emma, which is to just divide through first, since I can see that everything in row 2 is divisible by 3, everything in row 3 is divisible by 2. So why not make the numbers a little bit smaller in case I have to make some further manipulations later. So I'll change row 2 to 1/3 of row 2, and I'll change row 3 to 1/2, or maybe even minus 1/2 of row 3. Okay.
Well, not really, because when you're going to add, it's convenient. It's easier to add, and you will have like a negative and a positive.
Yeah, that's fair. Yeah. I was thinking of just having the
It
aim
was
of
the
noticing
one.
that two rows are the same. But yeah. Okay, so what do we get? We're going to get 0, 1, -1, and -27 here. And in my third row, I'm going to get 0, -1, 1, and 27 here. What do you know? Okay, so what's my last step going to be here? Should be pretty obvious.
Real question. You need to tell Sean what to do. It's not in raw echelon form yet. There's one more step. Can you tell us in the chat what the last step would be?
Yeah, thanks everyone. Yeah, that's it. So we've got a pivot entry at the top. Our next pivot entry has become a 1 now. But to make it to make sure we're in row echelon form, we need everything beneath that second pivot entry to be 0. So yeah, we'll add row 2 to row 3. But of course, as I'm sure you could see coming a few steps away, this third row is going to become just a 0 row. Yep. Okay. And are we in row echelon form now? Yes, we are, right? So there are my leading entries. There's no leading entry in the third row, which means that I've satisfied all conditions because every leading entry that appears in a row lower is further to the right. Okay, so I'm nearly done here, right? But I also need to solve, give the solution to this system of linear equations. And so how do I draw a solution from this? Well, first I look at my overall row echelon form shape, and I notice that there are no leading entries in the final column to the right of the dividing bar, right? So I know that there's at least one solution. It's not an inconsistent system, right? And furthermore, not every column to the left of that dividing bar is a leading column, right? The third column is lacking a leading entry. So that tells me that there's going to be infinitely many solutions, okay? So I can start off by introducing a parameter, and the parameter I'll introduce can be associated with the column that's missing its leading entry. So I can say, since the third column is missing, has no leading entry, we will let the corresponding unknown, so we'll let z be lambda, okay? Some scalar, or any scalar lambda. And just by setting z to be the parameter like that, I can work backwards up the earlier rows to sort out what y and x will be in terms of this parameter as well. Okay, so from row 2, what do I know? Well, I can read off that y minus z, which is really just y minus lambda, is minus 27. Yep. So that tells me that y is lambda minus 27. Okay, and that's good enough. That gives me y in terms of the parameter. So I know enough about y now. What about x? Well, I'll use the top row, row 1, and reading off again, that gives me that x plus y plus 2z, which I now know to be x plus lambda minus 27 plus 2 lambda. I know that that must equal 126. Yep. And so with a little bit of rearrangement, I will get that x is just 153, I think.
Yes.
Yep. Minus 3 lambda. Okay. Okay. So there's my full solution. In fact, so z is lambda, y is lambda minus 27, and x is 153 minus 3 lambda for any parameter lambda. Okay. So if you like, you can write out your full solution again altogether, but I'll just leave it at that, like that, I think, for now. Are there any questions about how that it was derived? No. Okay. Well, let's pretend Andy speaks for everyone and that no one has questions here. I think again, this is pretty standard so far, right? So let's look at part 3, and I wonder if I can maybe make a copy and drag it down.
Jeremiah, if you want to ask your questions while Sean is playing with the technology.
Yes. Regarding the lambda, what would that mean if? So that just means that there's going to be multiple solutions then, if that's the case, if we're just
Yeah, that's
ending up
right.
in lambda.
Exactly.
So
Yeah.
we can't really have like just one way of. So that means we still cannot answer the question, pretty much. Thanks, Andy.
Yeah. So we found the most general answer, right? This answer tells me that if I decided lambda is 10, then I can work out that I'm making 10 lots of the nutty, I think, cereal, and 10
10
minus
would be a bad
27.
idea because y is negative.
Yeah, that's right. Yeah. So, but the point is, I can pick any lambda, and it will give me some z, y, and x's. Maybe they won't make sense, but they'll definitely satisfy the three equations. And if we're lucky, there will be some lambdas out there that do make sense for the.
Actually, it's a good thing. It means you have a little bit more freedom. You can make another decision, on introduce another reason why you'd want another constraint, and then pick the lambda that suits you best.
Also, lambda has to be greater than 27 as well. I would possibly even already encounter a bit of a range here as well, because lambda has to be greater than 27.
I think you're doing question 3 for us.
Yeah, that's exactly right. Yeah. So part 3.
I'd like to go ahead with 23. Thanks.
Yes. So part 3 basically tells us, it says that we want to find a solution that maximizes the number of bags of nutty of n, which we said was z, right? And exactly the way that we're going to find this maximal value for z is going to be by working out what this restriction on the range is, based on the real world example of this being numbers of cereal, and so we can't have a negative number, right? So let's start off with that. The idea with these sorts of questions where we've got some parameterized set of solutions, but we want to find a maximal solution or something like that, is to work out what the natural restrictions are that will introduce this maximizing or minimizing factor, right? So in this case, what do I know? Well, I know that since x, y, and z, that they're numbers of bags, right, of cereal, it makes no sense for them to be negative, right? We can't make a negative number of the fruity cereal or whatever. So we can say that we know that x, y, and z are all greater or equal to 0. Okay.
And integers, 12.
Yes, that's true. Yeah. So the question further specifies that they won't make partial bags or something like that. So I don't think we'll use it in this question, but we also know that x, y, and z are integers. Okay. So in fact, we could say that they belong to n if you have encountered that terminology. But so let's use this fact, right, along with the solution that we found, right? So I have that. So z is greater than or equal to 0, but by my solution, that means lambda is greater or equal to 0. Whatever value I pick for lambda, we've said that we could pick any real value for lambda, but we want to restrict now the possible values for lambda to those that force the number of cereal boxes to be positive. Okay. So I need z to definitely be greater than or equal to 0. I also need y to definitely be greater than or equal to 0, which means that I need lambda minus 27 to be greater than or equal to 0, right? Or lambda needs to be greater or equal to 27. Okay. And my third restriction, that x needs to be non-negative, tells me that 153 minus 3 lambda needs to be greater than or equal to 0 from my solution to part 2. And rearranging and dividing, that tells me that 51 is greater than or equal to lambda. Okay, so these are my 3 restrictions on the parameter, and I want to sort of combine them into one. Well, yeah. So there are a few ways you can go from this point, right? The big question, the thing we're trying to answer, is we want to maximize the number of bags of nutty, which is to say, we want to maximize z, right? And because of the way that we went about with this question, we set z to be lambda, right? So maximizing z is the same problem as maximizing lambda, the parameter in this case. And so if these are the three restrictions on lambda that I have, can anyone find the largest such lambda that will satisfy all three of those equations at the same time? Yeah, if lambda is 51, it will satisfy all three equations, or inequations, right? Because it's certainly bigger than 0 and bigger than 27 and less than or equal to 51. And I can't get any bigger without violating, well, that last inequation in particular, right? So, so sort of combined, I have this restriction here that lambda has to be between 51 and 27 if I'm going to have a positive number of bags. And so the maximal value for lambda, which lucky for us happens to also be z, is 51. Okay, and so that means that the maximum number of bags of nutty would be 51. Does that solve the problem? Well, you might argue that this question is saying find the solution, which maximizes the number of bags of nutty. So the solution should tell me all values x, y, and z, right? How many? I know now to make 51 bags of the nutty cereal, but what about how many bags of regular and fruity am I making? So I should substitute this value for lambda back into my equations for y and x to come up with the full solution. Okay. So when lambda is 51, I have that z is 51, of course. Y becomes 51 minus 27, right? Which happens to be 24, right? And x becomes 153 minus 153, it becomes 0. Okay, so that's my full solution, right? I want 51 bags of the nutty cereal, 24 bags of the fruity, and as it happens, I want to make no bags of regular if I want to maximize the number of bags of nutty. Okay. And that's about all you need for that question. Are there any questions about how that part worked?
And so again, you can see that the only part you hadn't seen is how to apply row reduction to to a system of. The only new part was to use common sense, read the story, and then realize that a number of bags cannot be negative.
Yes.
Why do we want to find x, y, and z? Because it says the solution. It's the solution to the system of equation, and also,
Yeah.
so the solution really is made of three parts.
Yeah. So we found lambda. So technically, we've you could say we leave it to the reader to substitute in the lambda to those three values, right? But if you could argue that just by finding lambda, you're saying I know z is 51, but I should really tie down exactly how many of the other zeros we're making. I should probably spell out what y and x are as well, right? That's what I would do. If someone's asking for a solution to a linear system, that means they want all three values, or all n values, right? Now, as for how this exam worked out, I haven't seen the marking scheme, so I don't know if reaching lambda equals 51 was enough.
I think we probably, I don't remember. I think we probably gave the mark for those who only found lambda, but really the question specifically asked for the three. And also when you have a question about a real life story, usually your answer should be in terms of the real life story, because what's going to happen is people have a problem, they send it to a mathematician, you solve it, and then you tell them in plain English how many bags of each they produce. So probably in a question like that, your ideal solution, if it was an assignment, wouldn't have an x, and after that you would have just sentences with no x, y, z.
Yes, yeah, I agree. So in an assignment situation, you would absolutely be expected to write out the full solution. In an exam situation, I'm sure once you've reached that lambda equals 51, you've essentially solved the problem. You've demonstrated what the question needed you to demonstrate. So that would probably have been sufficient.
But technically, yes, they are asking for x, y, z.
Yes. Oh, and just before we move on to another question, I just wanted to point out, if you're using sort of meta exam technique, if you looked ahead with this question and you saw in this part 3 that it's asking you to take your solution and find a maximal such solution, right? That's implying that your answer to part 2 should have had an infinite number of solutions, right? It should have been parameterized, because if in part 2 I had found a unique solution, then part 3 wouldn't make any sense, right? I wouldn't be able to maximize a unique solution. So if you read ahead and saw part 3 and said, I expect to find infinite many solutions to part 2, then you'll know if you go off track. If you accidentally make a mistake somewhere and don't find that there are infinitely many solutions, you kind of have this cross-check to confirm.
So will the exams of the term 1 paper? No, I think the answers won't be released, because what happens is once we release the solution, people tend to just read them and not actually do the problem. So I think it works much better if people work on them and then they come to consultation. Or right now, if we do it in a live stream, you're really actually thinking and not just listening to what we do. You participate, you have questions, it's much more active. So I think there's no plan to release them, and an active plan to not do it, not just because we run out of time. So no, they won't be released.
Yeah, but as Laura said, if you've gone through them carefully and you have questions about certain parts of other exams, you can always bring them to the consultation hours.
Yes, absolutely. Yes. The 2019 exam gave you an idea of what the exams look like now. As I said at the beginning, the format of the final exams changed when we went from unseen class tests to lab tests. And also when we reduce the number of questions to give you more time to think.
Yeah, so of course the format will be a bit different this term, just because it will be an online format. But yeah, you can expect the questions to be of a similar vein, right? Not so much calculation. I mean, there's calculation elements, but most of the questions are sort of asking you to demonstrate that you understand the concepts introduced in the course.
Okay, so let's move on to question 2C. So we are given some maple output. And so we see that here we're given a polynomial, and it's the same as this one. I have to say that when I see these coefficients, they're so ugly, I'm delighted. No one's going to ask me to perform any calculation or very simple one with those, right? Let's be human. Okay, so perfect. So probably all the hard calculations have been done for me by Maple, very probably. So this tells me there's a polynomial, okay? And that tells me if I sub in 1 plus 3i into this polynomial, I get 0. Okay, let's go on to see what they want exactly. Show that z minus 1 is a factor of that polynomial. Yeah, how? How do we show that z minus 1 divides some polynomial? That's a very classical question. You should have an idea. You sub in, absolutely. If you want to prove that z minus 1 is a factor, sub in 1. Z minus 2, sub in 2. Z minus alpha, sub in alpha. So I'm going to calculate P of 1. And so I'm going to get 1 minus 13 plus 81 minus 317. So really, I sub in 1. In theory, I put this in my calculator. Really, they said show it is. So unless they made a mistake, I'm going to get a 0. Okay, I put it in my calculator. We get 0, right? So if you sub in 1, you get 0. So what's the name of this theorem? By the blah, blah, blah theorem. It would be nice if we could give its name. Z minus 1 is a factor of P. When there is so little in the question, maybe we would like to be precise. Can I get some help? The remainder is when you're doing a definition. This one is the factor theorem, which you use to factorize. The factor theorem tells you that if you're dividing by z minus alpha, so something of degree 1, then you can get the remainder without actually doing the division. Just plug in alpha into your polynomial. So that was an easy one. Okay, so we found a factor, that z minus 1 was a factor. Next question is harder. Find a real quadratic factor of the polynomial. So real quadratic factors, I'm sure you've done this for a lot of polynomials where you were actually finding all the roots of the polynomial. And in that case, I just look at that thing. It's of degree 7. The coefficients are just ugly. No way I'm going to find all the roots. So I can't find all the roots, but do I have any roots? Let's just summarize what we have. Do we have some roots of this polynomial? Yes, so someone's ahead. Yes, we have some roots. So we have, yes, so we know that 1 plus 3i is a root. Thanks, Maple. It's been subbed in for us. Yes, 1 is a root. We did that in the first question. And somehow Chloe says that we're getting another root, which is 1 minus 3i. Why would that be? We didn't try to sub in 1 minus 3i. The roots are conjugate of each other if the coefficients are real. Absolutely, exactly. That's all we need. So let's write how we know that. So 1 plus 3i is a root of the polynomial by the maple output. So the maple output are there to use, right? So you can use them right away. And so 1 minus 3i is also a root, since the coefficients of the polynomial are real. If you want to say it's a real polynomial, it's shorter. I started my sentence this way, so I'm finishing this way, but there was something shorter. Of the polynomial are real. And from there, it's a very classic technique. So I'm going to rewrite it with the exact same notation we have in the notes. So if alpha is a solution, and the coefficients of the polynomial are real, then its conjugate is also a solution. How do you build a real quadratic factor from those? And remember, we only need to find one. So you use the conjugate, yeah, but if I want to use a quadratic factor, I really need a polynomial in the end. So whenever you have this, blah, blah, blah times blah, blah, blah is a real quadratic factor. Do you know how to build it? Multiply them. If I just multiply the roots, sorry, I'm being picky because I think part of math is to learn to use the verb. Yes, z minus root times z minus conjugate. Perfect, thank you. Okay, so yes, that's exactly how you build them. So in that case, as long as you know one of them, that's enough. So if you multiply those two, some people know the formula by heart. I don't have enough brain space for that, so I just expand z squared. Then I put together the terms with a z in it, so I get minus z alpha minus z bar alpha. And then I see plus alpha alpha bar, so that's the square of the conjugate, so that's really z squared minus 2 times the real part of alpha times z plus the square of the modulus, and then my alpha was that. So z squared is z squared. Can anyone write me what I get when I expand? You can get alpha is a number up there, you can get its real part, and you can get its modulus, I'm sure. If you finish the calculation for me, what do you get? Z squared minus 2z plus 10. Oh, we have different answers. So I agree, the real part is the 1, so minus 2 times 1 minus 2z. And if I want to calculate the square of the modulus, remember what I do, square the real part and square the imaginary part. I think I totally agree with the 10. So z squared minus 2z plus 10. And so we got one real quadratic factor, but that's what the question was about. So the idea is they give you one root, and you have to know that if it's a real coefficient, then using a root and its conjugate, it's possible to build a real quadratic factor. So see, this one is not very different from the other example you had in past paper. I think the new thing with the new format is in 2019 is that Maple is actually giving you the root. I would argue it's easier. You don't have to agree with that, but I think it's fewer calculations. Questions on this one? No? And I saw somewhere on the chat, I don't know who said that, if you have a doubt about the past papers, yes, posting them in the forum is usually a good idea because everybody's working on the same past paper. They probably have the same questions. So it's a very good place. Okay, so Sean, maybe I'll let you take over. The next one is a really great one. I really like it. So Sean got a great one.
Okay, yeah, I agree. It's interesting. I'll be interested to hear your thoughts on how I write it up as well, Laura, because I imagine there's more than a few ways to think about this one. Okay, so this is question 2, part D. This was in the 2019 paper. This would have been the last algebra question, right? The end of question 2. There's a question 3 to come, of course, but that's all calculus. So you might expect that this is possibly the hardest of the algebra parts, right? And you might, once you've seen the solution, you might not even agree, right? You might think that that first one we looked at, question 1, part E, might have been trickier. But it's something to keep in mind that there's usually a gradual increase in difficulty. So what might make this question in particular so difficult or like less familiar? Well, I guess the main tricky thing we're dealing with here is that all these matrices we're talking about are in the abstract, right? We're talking about an n by n matrix B, but we don't really know much more about it. We can't draw an example matrix because we don't know if it's 3 by 3 or 100 by 100, and it's not going to be easy to manipulate it element by element, right? Entry by entry. So the idea behind this question, we suspect, is that we're going to be only dealing in abstracts, right? Just using the letter B to represent the matrix and never actually writing out a matrix or doing any actual calculations with matrices, right? As in row by row or whatever.
But that's not necessarily harder, because that means they're going to highlight for you the information you need and exactly the information you need, and you won't get any row operation wrong. So once you go past the psychological problem of saying it's abstract, I don't know what it looks like, I think this one is not too bad.
Yeah, that's right. Yeah, I agree. So when I see these ones, I know often when students see problems like this that look like there's nowhere to sort of start, they can get a bit worried. But yeah, if you think like the way that Laura suggested, everyone's in the same boat, right? No one can really get their hooks into this problem. So you can only use what you've been given, and there's not that much that you've been given here, right? So let's get started here. For part I, we want to find a non-zero solution to this problem. Bx equals 0. Okay, what do we know about B? Well, only that it's an n by n matrix, and that it satisfies the property that if there's this vector, there's some particular vector y that exists that allows for these two things to be true. So by is not 0, but b squared y is 0, the 0 matrix. Okay, or vector. So but we don't quite have that, right? We're dealing with bx equals 0. But as I just said, we want to use what we've been given, right? So what do we know that kind of looks like this? Well, we know that b squared y is 0, right? Now, can anyone suggest maybe another way that I might like to write b squared y that might help me get something that looks a little bit more like my goal here, b times something equals 0?
And I just want to point out that Sean's start is very natural. They're telling you, find a solution. Well, you can't solve because you don't know what B looks like. So the only way of finding something, so you need to find a concrete solution. So that means you need to have a vector. The only vector that's been given to you is y. So you know you need to use y. You want to solve something equal to 0, so you go back to what you know about y. And there is something that involves y and ends with equal to 0. So you just write this down. And then yeah.
Because there's two things that involve y, but the other one only tells me something that doesn't equal 0, so that's less likely to be useful, right?
And the answer's in the chat, I can see.
Yes, so a few people have written now. Why don't I expand this out a little bit to make it look a little bit more familiar? So b squared y is really just bby, right? If you prefer, you can stick some brackets around here, but of course we know matrix and vector times matrix multiplication is associative, so the brackets, the order in which we do things, so long as they kept in left to right order, doesn't matter. So in particular, right, it might be better to write this like this. Okay. And why have I written it like this? Well, because now it looks exactly like what I'd like it to. I'd like an expression that is b times something equals 0, and now I have that b times something equals 0, right? So I know that this thing, by, is a solution. Oh, maybe I'll write it so x equals by is a solution to bx equals 0. And now I'll go back to what the question's asking me and check that I've ticked all the boxes, right? So I found a solution, so that's good, right? Is it non-zero? Do I know that this solution is a non-zero solution? So yeah, maybe I won't leave it for the chat to put it out because it's probably pretty obvious to everyone, right? Of course, it's written right here in the question.
Yes.
The question tells me, right, that it's not 0. So we are told that by is not 0. And the other thing I should make sure is true is that this solution for my x is an n-length row or column vector rather. So I should know that it's an element of Rn, right? And is it? Well, y is an element of Rn. B is an n by n matrix. So yes, by, right, which is an n by n matrix times an n by 1 matrix will indeed give me an n by 1 matrix. Okay, so all the conditions I needed to satisfy are satisfied. I found a solution to this thing, bx equals 0, that is not 0 itself and is in Rn. Okay. Any questions about that first part? Hopefully everyone's. Oh, yeah, Jeremiah has a question.
So when you said that there's the n times n and n times 1, so would that mean that the solution, you said, just to make sure, you said that the solution was going to be an n times 1 matrix as well. So should I just
the result of the product is what you meant.
Yeah, so you might remember when we multiply two matrices in general, if the matrix is say m by p and p by n, then the result will be m by n, right? So
n by n.
Yeah, so the rule in general when you multiply two matrices is that the number of rows of the first matrix is the number of rows of the second matrix, or the result matrix, and the number of columns of the second matrix is the number of columns of the result matrix. And then the other thing you need, of course, is that the number of columns of the first matrix is the number of columns of the second matrix. So they you can kind of imagine the p's as canceling, kind of.
So maybe what
That'll still take some time for me to understand, actually.
Sorry, what was that?
Now, that might take a wee bit of time for me to actually understand when I think about it. So you said, yeah, actually, I'll try and get that down. But yeah, thanks for that.
Sure.
Just make sure you don't rub that out. I'll give it a
Okay, sure. Yeah, okay.
So what we're saying here is that you can consider a vector with n entries as a matrix which would have n rows and 1 column.
Yes, that's important. Yeah. So yeah, well, we'll leave that up. Hopefully that kind of explains it. And the fact I wrote up in red up the top is one that we are assumed to know well, right? Because we sort of we cover that when we talk about multiplying matrices in the first place. So okay, so let me move on to part 2 for now. Where we want to say something about the determinant of B. Okay, so determinant should be pretty fresh in your memory since it's the very last topic of the algebra course for 1131. And you might know a few facts about determinants, but in general, things we know about determinants tend to have to do with whether determinants are 0 or non-zero, right? And so I might suspect that this question, if it's asking me to say something about the determinant of B, probably I want to conclude that it's 0 or it's non-zero, right? Maybe I can say more than that, but that's a good place to start. Yep. So, and this is where I suspect that there are quite a few ways to approach this, right? There is, in fact, even a proposition in the notes that you could use to immediately say something about the determinant of B. But I'm going to pretend that I don't know all the propositions from the book by heart and try to sort of derive some information about it. Okay. So when I think about determinants of matrices, I think of them as ways of sort of flagging whether the matrix is invertible or not. And so what I might try to do here is determine from the facts I have whether B is invertible or not, because that will immediately tell me whether the determinant is 0 or non-zero or not. Okay. So the way that I think is a good way to start here, right, is to pick, right, to decide, like B is either invertible or it isn't. Maybe we can work out that it has to be invertible or it has to be not invertible, right? But let's just start by supposing that it is invertible and see if we can determine anything or deduce anything from that. So I'm going to say, suppose that B is invertible, which is to say that there is a matrix B inverse with the usual properties of an inverse matrix. Okay. Well, if that's true, right, then if I start again with the equation that part 1 was interested in, right, this equation that bx equals 0, once I assume that there is an invertible matrix for B, well, I can pre-multiply both sides of the equation by B inverse, right? And why is that useful? What will I get as my next line here? Someone in the chat? Yeah, thanks, Jonathan. So B inverse B, right? Why did I introduce the inverse? Because I know that the one useful property of it is that it inverts the matrix when I multiply it by its inverse, right? So B times B inverse better equal I, right? Which is just the identity matrix. So I can really just write that as just X, right? And the right-hand side is going to be what? Well, it's just some matrix times a 0 vector. It's still going to spit out a 0 vector, right? Yeah, so if an inverse exists for B, then the only solution to Bx equals 0 is that x equals 0. Okay, because every step I made was not eliminating any possibilities, right? All I did was pre-multiply by an inverse, and I found that if this inverse existed, the only solution to this system Bx equals 0 is the solution x equals 0, right? Now, of course, I know this not to be true, right? I know that there's at least one other solution out there, By, which is not 0, right? So let me say here, but we know there is at least one non-zero solution. Which we found in part 1, right?
Sorry, I written stuff, but I moved them, but there's some lag, so that's why they're still on your screen.
Oh, sorry.
Yeah, you can erase all of that.
Oh, I see.
Because that's what was in the notes, so it was just the shortcut.
I see, yeah. So, well, I think I can just fit above what you've written, actually. So, so the point is, we know that our supposition was wrong, right? What we supposed can't be true. So it must be true. It must be that B is not invertible, right? Which is the same as saying that the determinant of B is 0. Okay. And Laura has written in red fact
Yes, so it's
that.
half erased. Now, half of it is there, and just erase it on your screen maybe, because it's deleted on mine, so it's going to disappear on yours anyway.
Oh, okay.
You have
Okay,
the
sure.
same thing below, but much below.
Oh, okay. Okay, cool. So this is the way that I would deduce this fact, right? And if you there we go. Yeah. So if you remember from your notes, or you might have been like seen this in lectures as well. We can also make these deductions very quickly without having to sort of show the steps between. If if you remember these facts, right? So as Laura's written, if you know that a matrix has zero determinant, then I guess we should say yeah.
Non-zero.
Yeah. So if you know that matrix A has a non-zero determinant, you know it's invertible. It's an identical statement, right? And that's identical to saying that the equation AX equals 0 has a unique solution. Okay. And what is that unique solution? It's x equals 0, right? So we just showed we had a system Bx equals 0. We found in part 1 that it does not have a unique solution. There was at least one non-zero solution. And so following this chain of implications backwards, but sort of the reverse, we know that A is not invertible, and so its determinant must be 0. Okay. So and this is why I was interested in what Laura might have to say about this question, because I wondered if it would be enough to just quote the proposition that turns up in the notes.
Yes, I think you either quote it if you know it, or you reproved it. You said if it was invertible, 0 would be the only solution. But look, above we just saw that by was also a solution, and it's not 0. Therefore, it's not invertible.
Yeah,
and
that's right.
This type of question, in some sense, you could say they're easier than another question about determinant, because to approach determinants, you could do calculation or you could use theoretical results. In this exercise, you're not doing any calculation, so you know that what you will be using is this kind of theoretical result, and it shrinks down the number of tools you could be using. You could say it's pushing you in the right direction.
Yeah, that's right. Oh, so I guess I should check
in the last minute.
Yeah, okay. Let's squeeze in part 3 here. And so part 3 you can also very quickly answer if you refer back to one of the propositions, that's a similar proposition to the one that Laura was quoting. But let me show a way that you might do it if you don't remember all these propositions off by heart. And let me just see if I have copied. Yeah. So here we're going back to the equation b squared x. So b squared x equals 0, and we want to solve for x, right? And we want to show again that it has infinite many solutions, right? Well, this system b squared x equals 0, it's a linear system, right? So maybe let's say since this is a linear system, we know for sure, we know for a fact that there are 3 possible results, right? So there are, we have 3 options. There can be no solutions, there can be a unique solution, or there can be infinitely many, right? And this question has told me, oh, something funny is going on with the text over there. I don't know if that's, well, I think we can all remember what's happening there. So what I want to do here is I've been told, right, that I want to show it has infinitely many solutions, right? I know that my goal is to show there are infinitely many. And so since I know that it can only have no solutions, exactly one solution, or infinitely many, if I can show that there are 2 or more solutions, then I'm done, right? It has to fall into that third case, and so there must be infinitely many. So my question to you is, to the chat is, what solutions do we have to this equation already? I think it's a really easy one that you can see quite quickly. So remember, we're trying to solve for x. Yeah, right. So Michael's given, I think, the harder one to spot.
Yeah, the hard one, yes.
Yeah. So by
Not really by, because now see the equation, there's a b squared. The matrix is b squared.
Oh, that's right. Yes.
And we're multiplying by something. But you're really close. So Michael, can you modify this a little bit? Because you already have the b squared. So what should you put in place of x? Y. Yes, exactly. So that's one solution. That's the hard one. Something obvious.
Yeah,
Zero.
yeah,
Yes, absolutely.
yeah.
Zero would work.
So yeah, so one solution is I'm going to write the easy one first, right? It's x equals 0, right? I think that's obvious. I think it's safe to just write that and leave it there.
We mean the zero vector, of course, not 0, because I said
yes,
0 too.
right.
So
yes, true. Yes. And another solution, as we mentioned now in the chat, is x equals y, because b squared y, we saw in part 1, can be written as b times by, and we know that actually,
b squared equals b squared y is 0 is given as is.
Yes, that's right. Exactly, yes. Is given. Now, the only thing I have to make sure now is that this really is a different solution to the first one, right? So do I know that x equals y is a different solution to x equals 0? Or can someone give an explanation for why I know that? Yeah, thank you, Shalindra. Yeah, yes. So because, well, if I'm stuck, I can go back to the top of the question and just check what information I've been given, right? And you might remember I was told two things. I was told b squared y equals 0, which I've used. The other thing I haven't used, which I was also given, is that by is not 0, right? So those are the two facts I was given, and I've used them both. And yeah, obviously, if by is not 0, y itself can't be 0, because
if y was 0, then by would be 0.
Exactly, yeah. So that's all we need, right? We found two different solutions, which means we can't be in this case where there are no solutions. We can't be in this case where there's a unique solution. We must be in this third case where there are infinitely many, right? So there are infinitely many.
Okay, I wouldn't say b squared y is a solution. So when you solve the equation, you need to find x. That means you're trying to find b squared times what? Gives me the 0 vector. So it turns out that b squared times 0 gives you the 0 vector. So 0 is a solution. That's what we write when we write x equal. We're just trying to say is a solution. And if you sub in y, you get b squared times y equal to 0, which means that y is a solution. So maybe what confuses you, Emma, is the fact that we're using the letter x. But just like if you solve 3x is equal to 5, you could write the solution is 5/3, or you could write x is equal to 5/3. And usually we write this as a solution. So that's what Sean's been doing here.
Yeah, so the idea is we're trying to solve this equation, b squared x is 0, which means we're trying to find x's that solve that equation. So one of the x's that I can plug up into here is when x is 0. Another one of the x's that works is when x is y. But yeah, I always think of we're trying to find x's that solve this equation.
And I'm thinking maybe Michael is the one who answered the question. B squared y equal to 0 is given in the question. Yes.
Yes, yeah. Okay, so hopefully that kind of explains that one out. And as I said, you could also use Laura's argument in the red pretty similarly here, I think, as well.
For the last question, I would have done what you do. I think it's clear and simple. There could be 0 solution or 1 or infinitely many. Well, if there are 2, then it can only be infinitely many because it can't be the others. I think it's
exactly. Yeah,
exactly.
And I think that's how that feels like what the question is pushing us to do, I think.
Yes. So do you have a question on any of that? And as you can see, we're trying to do more than just give you the solutions. I'm trying to re-explain why we don't just print perfect solution. We're trying to explain how, by looking at the question, where we start to get some idea about to approach things, which is also why it takes longer than if you were actually just doing it.
Yeah. So Caitlin asks, how is x equal to y when x is so
It's different x's.
yes. So yeah, I'm finding different x's to solve for this problem, right? It's like saying solve this problem here. Solve x squared equals 4. We would say, well, x equals 2 is a solution, x equals minus 2 is another solution, right? But yeah. So in this case, so case 1 and case 2 are different x's that solve the same problem. Explain part 2. Yeah. So the thing is, so again, I'm dealing with this equation. I'm trying to find solutions to this. B squared x equals 0. I'm trying to find x's that
I
can
think
be
what's the
substituted in
confusion with
0.
your x? You want to put an empty box instead of x? Maybe that would help.
Oh yeah, it's a good idea. Yeah. Okay. So I'm trying to fill in this box, right? If I'm solving for x, it means I'm filling in the space where x currently sits, right? So I'm trying to find things that will go in that box that solve the equation there. And so in part 1, we can see, oh yeah, obviously one solution is if I just stick 0 in here, right? But what we'd like to do is find at least one more solution. And so I think back to the start of the question, and I think, what have they told me about b squared? Well, the question told me that b squared y equals 0, right? And so, hey, that means that y can go in this box. Yep. Which is to say that one solution is, well, it's that the box can contain y, right? But remember, the box is really just standing for x. Cool, so that explains that. Okay, yeah, good. Yeah, that's a bit. It's a bit tricky just keeping track of the terminology, right? But yeah, if it's solving for x, that means that x is just sort of a blank space that you're trying to fill in. And all we wanted to do here was show that there are at least 2 different things that could go into that blank space, because then there had to be infinitely many.
Do we have any more questions? Okay, so thanks everyone. Thanks to all the ones who gave answers in the chat, and thanks to all the ones who asked questions when they were confused by something we did, because this really helps clarify things. And so we'll see you this week during consultation times, I'm sure, or on the forum.
Yeah, thank you, everyone.
Thanks. And thanks, John, for starting the recording.
Yeah, that's all right. I spotted your reminder. All right, yeah, thanks everyone. And yeah, as Laura mentioned, the consultation hours will have switched starting this week. So there'll be more people available for each session, but make sure that you check the timetable on the consultation Moodle page to make sure, because I think we'll only be, I think the slots are, well, for most days, the slots are 10 to 12 and 2 to 4.
Yes.
Yeah, so keep that in mind.
Yeah, so thanks everyone. Oh, the bonus question, I was thinking that in case we finished too early, I added a question, but it was not from a past paper. It was a little bit more trigonometry, because I think that trigonometry is not always taught the best way in New South Wales, and I'm working on fixing that.
I think, is that bonus question taken from your slides, Laura?
Yes. Yes.
Yeah, so if you want to, well, I guess we can show it quickly now, but you can, that's what it looks like. And if you want to find a copy of it later, you can look at the slides for the Jonathan Kress and Laura Guizon lecture stream.
Yeah, so we didn't have time to do it in class, which is why I put it there.
But yeah, that's a bonus question if you haven't seen it already.
Okay, well, so thanks, Sean. And
Yeah, thanks you all.
yeah, bye. I'm going to leave.